activate and allocate different numbers of cells to form the memories that this now is forming and going to use in order to organize where it goes in space and presumably remember where the shock was. Well, we might now ask, that was the easy question to answer. We might now ask, how do the neurons remember whether or not they should be active? And in order to study that, what we understand is that the synapses, the connections between the neurons, these are the things that actually differ, and they can change with experience. That's the dominant hypothesis for answering the question, how do the neurons remember whether or not to be active for one memory or another memory? And now let's talk a little bit about the neurobiology, some of the findings that support that point of view. The story begins with an important paper by my colleague, Todd Sackler, where he identified a particular molecule called protein kinase M-zeta, PKM-zeta. And what he was able to show is that it's necessary and sufficient for something called LTP maintenance. What's cartooned here is if you were able to make a measurement of the electrical activity of a single one of these neurons in the hippocampus, what you can see is and measure is how easy is it for that cell to generate an electrical current. And what we see here shown on the x-axis is time, and on the y-axis is shown the amount of current that could be measured from across a pair of these cells. And what you can see is that in one of them, starting at time 0, the current is going up, and then it stabilizes. It takes about 10 minutes to go up, and then it stabilizes. And the trace that shows the increasing current, what the folks at Todd's lab did, was they delivered into the cell protein kinase M-zeta. So it was sufficient to increase the electrical communication between neurons. And other experiments, I'll show you one now, that I did. PKM-zeta was shown here in the western blot with some control protein actin. What you can see is after 1 day or even after 1 month after the training, the levels of PKM-zeta have elevated. That's really quite remarkable because, again, I'm unaware of any other molecule that based simply on experience will have an elevated expression like that. Certainly no other memory molecule, again, that I'm aware of. So that's quite enticing. Experience itself is sufficient to increase the elevated activity, and it does so in a persistent way, lasting at least. And so where does PKM-zeta reside? PKM-zeta resides on the postsynaptic side of the synapse. And it's a molecule that engages and modifies other molecules that change the expression of the electrical response when one cell is active. The presynaptic cell is active and releases its neurotransmitter to the postsynaptic cell. And if we were to look and make slices, instead of grinding up the brain, make slices and stain the brain so that we can find out where is the PKM-zeta, we can see that after 1 month, in an animal that received this training, so 1 month later we can sacrifice the animal and look for PKM-zeta, and we see the hotter colors, if you will, on the right side of the trained animal compared to the control animal. The control animal had exactly the same experience, the shock was simply never turned on. So PKM-zeta seems to form some kind of a long-lasting trace, if you will, of the experience of the animal. We would imagine and work under the hypothesis that that's a trace of the experience, the kind of thing that we call a long-term memory, and how it's maintained. Right? So to actually test that idea, it's not sufficient simply to look and see that the molecule is there. We actually want to make a manipulation. And so this is a video I'll show you of an experiment that we did. And what we did in this case was we trained in this experiment, it was a rat. We trained rats on this rotating arena to walk around, first of all. In this case, the shock isn't turned on, the rat is walking around, the rotation is about 5 times faster, otherwise it would be very boring to watch. You'll notice that the rat goes everywhere, and we can track where the animal goes, and the computer can decide, based on where the rat is, whether or not to electrify the floor. And so we have training trials where the floor is electrified when the animal is detected in a particular part of the space, a particular part of the room. And it can know where it is in the room by looking at the cues that are on the curtain and such that aren't necessarily visible to you. The red mark on the arena is there just so that we can see what the computer has decided to shock. So now we can do the experiment. We can do a controlled injection just of saline into the hippocampus a day later and put the animal back and watch, does it express memory by staying away from that place that is shocked. And if it does, as in this case, you see that it runs away, it just enters and runs away. We didn't turn the shock on, presumably it ran away because it remembered the location of the shock. But what if we inject an inhibitor of TKMZ? What we see instead is the animal doesn't avoid any longer. It seems to walk around as if, in fact, it was naive for being in this arena. And in fact, as if it was naive, certainly, that the shock was ever delivered in the upper part of the arena. In fact, if we compare that same rat his first time in the arena with the time after the zip injection, it's very difficult to tell the difference. And this makes it look like it's possible for the first time to erase a memory. Because what we did in subsequent experiments is show that after this erasure, if you will, the animal had no difficulty to form a new memory. It could form short-term memories, and it could even form long-term memories after the zip had been metabolized a couple of hours later. So we hadn't damaged the brain in any way. And because it looked like it was now possible to edit, if you will, to erase memories, whether or not specific, this got the attention of quite a number of people in the public media, as well as our friends in the scientific world. In fact, that inspired some other researchers to test that idea. And they had a very interesting and reasonable approach. They said, well, if TKM-zeta is so important, if it's crucial for memory, then it should be possible to genetically delete TKM-zeta in a mouse. And if we did that, then the mouse should not show normal learning. It should not be able to acquire memories. It should not have the ability to remember. And it should not have the ability to make LTP, this long-term potentiation of the synaptic transmission between neurons. But as you can see from the titles of these papers, by deleting or knocking out the gene of TKM-zeta, and the mice were pretty normal. And they remembered well. So that led these authors to conclude that TKM-zeta was not crucial for long-term memory or LTP, and that in fact our inhibitor must have been acting on something else. So this is the nature of science, and what is interesting about science is that it breeds controversy. And with controversy it breeds further investigation. Very recently we explained how it is possible that by deleting the gene you could still observe that there would be normal learning and memory, when in fact that gene is indeed crucial for learning and memory. And I'll explain now in the next few slides. The answer was quite simple. In part one, I talked about how we need to think about complex systems like the brain and complex processes like memory at multiple levels of biological organization. And the answer was simple. There was compensation. When the gene for TKM-zeta was deleted, an alternative gene, another related, in fact very closely related gene, itself became expressed. And otherwise, in a normal or in a wild-type animal, its expression tends to be low or suppressed, presumably by the presence and actions of TKM-zeta in memory. So what you can see here is that this other protein called TKC iota-N, that they're part of the same family of proteins called protein kinase Cs. And if you look on the left, you can see that in a knockout mouse, when you take the half brain, the henny brain of that mouse, and you measure how much TKC iota-N is there, you can see that it's about the same. But if you look in the specific part of the brain, the hippocampus, that's crucial for memories, there's an overexpression by almost 60% of that particular molecule. This is just spontaneous. And in fact, if you look at the active form, this is the phosphorylated form of the molecule, you see that the increase is over 400%. So there was a massive increase of this other molecule, TKC iota-N. But that doesn't prove there's compensation. That just proves that there's a suspect. So we have to do work. The logic is, if TKM-zeta is crucial for memory in wild-type animals, but is compensated, and therefore the mechanism for memory and the mechanism for LTP is different in the TKM-zeta knockout mice, then we should be able to selectively inhibit the new synthesis of TKM-zeta to prevent LTP. I'll show you subsequently memory, but only in the wild-type mice. So you can look here at this trace along the x-axis is time, on the y-axis is a measure of the synaptic strength or the synaptic response to stimulation from the presynaptic cells and how the postsynaptic cells are responding. And at time 0, a strong stimulation is given to induce this long-term potentiation. And if you look at the wild-type mice in green that received a scrambled version of this inhibiting molecule, we used an antisense oligodeoxynucleotide, which is something that will bind to the DNA that's designed to interfere with the manufacture or expression of the new PKM-theta molecule. When we inject that, what we can see, or when we put that in the bath with measuring LTP, what we can see is in the green trace, when that oligodeoxynucleotide is a scrambled ineffective form, you see normal LTP. But in the red, you can see that the LTP is able to be induced, but it doesn't sustain. Okay? And it seems to have no effect in the null. So that's the first, if you will, piece of evidence that the mechanism for LTP is PKM-theta dependent in wild-type mice, but different in the knockout mice. Second is the complementary experiment. You can now try to inhibit the PKC iota lambda. And there was a specific inhibitor for that called ICAP. And you can see there, if you give ICAP the upper trace to establish LTP, when you add the ICAP, LTP goes back towards baseline and depotentiates, but only in the PKM-theta null mouse. That's not making PKM-theta protein. Whereas in the wild-type mouse, which can make PKC iota lambda as well as PKM-theta, this maintenance, that's the black trace. If you look at the open circles on the bottom, you see that second arrow at time 270 minutes. That's a second stimulation that we can give. And what you see is that it becomes difficult to establish the LTP. So PKC iota lambda has been known to be important for the initiation of LTP in memories. But it seems to not be crucial for the maintenance of it, at least with wild-type animals. But it seems to act as a backup mechanism when you get rid of PKM-theta through the genetic condition. What does this do for long-term memory? So what we can do is repeat these experiments.
さっき銀座線と間違えて入って今度ここから入るんで、
じゃあこれで浜松に乗っていくんですね。
はい、
じゃあそのままどうぞ。
The detention time it takes to first enter the shock cell is long, however, not after delivering the antisense to prevent the synthesis of PKM-theta. And in the PKM-theta null mice, these things have an effect. Those gray bars are quite tall, indicating good memory, as I showed you in the pictures of the previous. What about the PKC iota lambda inhibitor, ICAP? So now what we can do is train the animals to establish a long-lasting memory, both the wild type and the PKM-theta null mice. If you look at training trial 3, they both established the memory and they're staying away from the shock cell. And now, one day later, before putting them back in the arena, we can deliver the PKC iota lambda. Now, he goes everywhere and is acting as if it is naive. And that's also shown here in summary data. The dark bar is the wild-type mouse showing the memory or the measure of how long it took to enter the shock cell is very high in the wild-type mouse, but in the null, it's very short because it doesn't demonstrate memory. Again, evidence that the mechanisms of maintaining memory are distinct in the wild-type and the PKM-theta null mouse. In fact, what we can look at is the detailed behavior in the PKM-theta null mouse and ask if they actually learn in a normal way. If you look at the details of where these animals actually spend their time, you can see in the wild-type mouse, early in training, we give them a training protocol that's harder to acquire. Early in training, they spend their time through the red activity. That's the density of where the animal is spending its time, is across from the shock zone, around 6 o'clock. It happens to be there right on day 1, and in fact intensifies with training. But look at the PKM-theta null mouse. Like that red area is closer, if you will, to about 9 o'clock, and it only very gradually, it takes 7 to 10 trials before it actually moves. The animals decide to spend the time in the shade of the party. And if you look and quantify this, you see it takes the animals. You can measure the ratio of times opposite the shock zone, the safer part of the shock zone versus the safer part of the arena versus the part adjacent to the shock zone. You can can see here is that ratio is declining gradually in the wild-type mouse, and it's established already by the stay. However, again, they are different than wild-type. And we can look at a different memory task. In this case, what we can do is have animals walk around in 3 different boxes. Cartoon here is green, yellow, and blue, but they just look different. It's no difference for the animals. And what we can do is take advantage of the ability or interest of mice in different objects, and they respond to novelty. So the animals were made familiar with different numbers of objects in these boxes, and in the one case, what we can do is after they've been familiar for a day and stored presumably memory for those objects, what we can do is exchange the objects, for example, from context B, those orange objects, we can exchange them for a pair of the objects in context A, and put the animal back and look to see where the animals spend their time. Do they investigate the novel objects? If they do, just like the wild-type animals. And we can also ask, what happens if we just exchange a pair of the objects that were already in the context B? So you can see the circle has been exchanged for the cube in the yellow case, and this is a much more subtle distinction. You can think of the first distinction as if, for example, someone were to exchange your toothbrush for the fork at the dinner table. That would be something that would gather your attention. But much more subtle is exchanging the fork, for example, with the spoon. And that subtle distinction the animals don't seem to remember if they're missing the PKM zeta molecule, as in the case of the PKM zeta null mouse. And if you simply exchange the locations of a pair of objects, they have, again, very strong memory for that, no difficulty in recollecting that. So what I've shown you so far is that PKM zeta is crucial for the persistence of long-term memory. And you might ask another question. Are these just crucial for the persistence of long-term memory in normal wild-type mice? We might ask another question. Does PKM zeta actually increase in long-term memory if it's maintaining the memory? How does it do that? The simple, the most parsimonious way to accomplish that would be to make so I'll show you some experiments that you can see. Experiment has train animals form a memory. And in this case, we can train them to form a one-day memory. In place of what you task here, you see the control animals, the shock and the turned on, they're just walking around. Whereas the trained animals, they stay away from the shock zone. You measure how long it takes to get to the shock zone. It's elevated if you look at the dark bars a day later. And a day later, we can see that where the asterisks are, that the amount of PKM zeta studied by Westerblot is enhanced one day in these animals that had spatial training, whether or not they actually were tested for their memory. The elevation already happens 2.5 hours after the training, but it doesn't happen within 5 minutes in the animals they establish a short-term memory. So it takes some time for PKM zeta to get made and to be elevated, and then it can remain elevated persistently. The control experiment here is a group of animals received an unavoidable shock. So every time the trained animal was shocked, this group of animals was also shocked, and that doesn't itself increase the PKM zeta. It's really necessary to form a memory for the zeta increase. And that, in fact, if you were to look now at just the data from the animals that had the spatial training on day 1, and you were to measure how well they remember, shown on the y-axis, their time to center, and you look at the amount of PKM zeta that was expressed in the hippocampus, the x-axis, you see that there's a strong relationship. Those animals that express very low levels of PKM zeta in their memory retention show weak memory retention. Those animals that express very strong memory retention show strong memory retention. So it seems that PKM zeta both increases and is correlated with the expression of long-term memory. So how long does this increase last? We can repeat this experiment. And instead of testing 1 day later, we can test 1 month later. What you can see here is with this particular training, the animals show very poor memory recall 1 month later. They're going everywhere. And when you measure PKM zeta levels, you can see that the PKM zeta levels in green are no different from baseline. They're not decreased a month later when the animals show no memory 1 month later. The bars on the graph show the control animals who never formed a memory, and the animals that were trained for 1 month later also don't show memory expression. And PKM zeta also isn't decreased by Western blot. But if we train the animals a little bit differently so that they form a 1 month memory, as shown here, you see now the trained animals are staying away from the shock zone at the retention test. Even 1 month later, the gray bar shows that it's elevated. This is now 1 month after the
乗り換えです。まもなく大手町です。足元にご注意ください。出口は右側です。